should be recording for you. And so this is Miss Bennett's class. That way everybody on the thing will be good. All right, so we're talking about salts. Salts are ionic compounds. We have 4 ionic compounds here that we have to decide if they're acidic, basic, or neutral. Okay? All right, we're taking apart the salts into their ions and deciding where they came from. So Na plus came from NaOH, which is a strong base. So strong bases then have very weak, right? Very weak conjugate acids. They are so weak, they don't affect the pH. So this one is not going to affect the pH. The chlorine, what did it come from? The chloride ion came from what? HCl. Strong acid or weak acid? Strong acid. So again, this is going to be a very weak conjugate base. Is it going to affect the pH? No. And here's the thing. What's in the solution when you put salt in water? What are your major species in a solution of salt water?
Salt.
Okay, salt and water. But the salt exists how? In ions. So your major species are Na plus, Cl minus, and water. There's no Ka and Kb for strong acids and strong bases because we assume they go completely, right? Mm-hmm. So these are so weak that their Ks would be almost nothing, right? But water now dictates the pH because it's the only thing left in there. And water, right, autoionizes and ends up having a pH of 7, which is neutral. So this particular salt is going to be a neutral salt. Okay, until we get through this whole list, it may not all make sense. All right, look at the next salt. All right, so NH4Cl, so ammonium chloride. We have NH4 plus and Cl minus. What did NH4 plus come from? NH3. Weak acid, weak base, strong acid, or strong base? What is it? It's a weak base. It's a weak base. So the conjugate acid, which is what the NH4 plus is, it's stronger, right? I'm not going to say it's like a strong acid, but it is strong enough. It is a strong, weak conjugate acid. Does that make any sense?
Yes.
Okay. So it's strong enough to affect the pH, but it's not going to be you wouldn't call it a strong acid. But it is strong enough to affect the pH. All right. What did the Cl minus come from? HCl, which is a strong acid, so this one's not going to affect the pH. So that salt in solution will be acidic, basic, or neutral? It'll be acidic. Because this is the thing dictating the pH. Okay, how are Ka and Kb related? Do you know? They don't add up to 14. They multiply to 1 times 10 to the minus 14. So if you look at this to prove to you that this is the strongest one in our solution, Ka times Kb equals Kw. Ka, and you would have to look this up on a table. It's just this one we use all the time. So Kb for ammonia, I believe, is 1.8 times 10 to the negative fifth. Somebody Google and double check. But
that sounds like acetic acid.
I know. I think it's the same.
Okay.
I think they're the same. I think the Kb for ammonia is the same as the Ka for acetic acid. Will you Google it real quick and double check me? But I'm pretty sure it's the same.
Oh, the Kb of ammonia is 1.8 times 10 to the negative.
Okay, so we're good. 10 to the negative what? Okay, we're right. So it is. So the Kb for the weak base times the Ka for the conjugate acid will equal Kw. What's Kw? As long as we're at 25 degrees, right? As long as, and most of the time you're going to be. All right, so Ka of our conjugate acid is going to be 1 times 10 to the negative 14th over 1.8 times 10 to the negative 5th. Somebody do the math, but I think it's 5.7, 5.6, something like that, times 10 to the negative 10th. 10th.
So Kw is always 1 times 10 to the negative 14.
It is, as long as you're at 25 degrees. What?
It's like 5.55 times.
Oh, so 5.6. Okay, so 5.6 times 10 to the negative 10. All right, so when we look at a solution of NH4Cl, what are the major species in that solution? NH4 plus, Cl minus, and water. The Cl minus we know is not going to dictate the pH. How do we determine which one of these is going to dictate the pH? It's the one with the bigger K. It's the one with the bigger K. You just found out that the K for this is 1 times 10 to the negative 10. The K for water is 1 times 10 to the negative 14th. Which one's bigger? So NH4 dictates the pH, making it acidic. So do you see it math-wise now too?
NH4, is it not 5 times 10?
Oh, did I write it wrong? Oh, I did. It's 5.6. Yes,
Okay.
I'm not paying attention. Sorry.
Either way, it's bigger.
Yeah, either way it's bigger, but yes, I wrote it wrong. You're right. It's 5.6 times 10 to the negative 10.
So both of the ions that it breaks down into are strong enough to affect the pH.
Only one of these is.
But what if both of them?
Then we have to check Kas or
Okay.
Kbs.
So you
The one
can't
with the
just-
biggest K is the one that's going to dictate the pH.
So you can't just assume it's neutral.
Nope.
It's strong.
Nope. They will. On a test, you'll be given the K values. On your homework, you would look it up on a table. You have a table in the back of your book that has all the Kas. Uh-huh.
So how come you can't, how come you can assume for the NaCl that it's neutral for both weak, but you can't assume
Because they're so weak that they're going to be less than water.
me? Sorry.
So the Ks for those, although we don't have Ks, so I can't show it to you mathematically, because the strong acid and strong base don't have Ks. But think of them being in the millions and billions and trillions.
Okay.
If I take the 1 times 10 to the negative 14th and divide by that, I still get smaller than 1 times 10 to the negative 14th, right? So the water ends up dictating the pH. And when you take the H plus concentration from water, it's 1 times 10 to the negative 7th, so the pH is 7, right? All right, look at the next one. What is it split down into?
K
K plus.
plus and NO2 minus.
What did the K plus come from?
KOH.
Came from KOH. Strong acid, weak base. What is it?
Strong base.
Strong base. So do we care about it?
No.
No, it does not affect the pH enough to matter. NO2 minus, what did it come from? HNO2. Weak acid, strong, 2, not 3. Strong acid or weak acid?
Weak acid.
Weak acid. So this one is its conjugate base. It's going to be strong enough to affect the pH. The math is going to work the same way, right? So this one is going to dictate the pH. Oops, I pushed a button while I circled. And this one will be a basic salt.
So it's weak, but it's just strong enough.
It's strong enough to affect the pH more than water.
Why did we not have to look at why did we not have to look at the concentration of water against the KB? Not the Ks. Why did we have to look at the Ks this time?
Oh, you can. I was just proving the K's to you mathematically.
Oh, okay, so we didn't have to do it
You
last
don't
time.
really have to do it if you can think through this process. You don't really have to do it if you just qualitatively have to say if it's acidic or basic. If they asked you the pH of that salt, you would certainly have to do it. But just to tell me if it's acidic, basic, or neutral, you can just think through it. I just tried to prove it to you mathematically as well. Okay? All right, this one's the trick one. What does this break down into? NH4 plus and the acetate ion. All right, what did NH4 plus come from?
NH4.
NH3, which is a weak base. So this is a conjugate acid. What did acetate come from? Acetic acid, and it's a weak acid. So this is a conjugate base. Now we have a problem.
Strong and strong.
Sort of strong, sort of strong. They both can affect the pH. What do I have to do to figure this one out? I have to do the math. Okay, for sake of time, will you believe me if I tell you they both have the same math, because it happens that the Ka of acetic acid is the same as the Kb of NH3? So both of the conjugates come out with Ks of 5.6 times 10 to the negative 10th. So both of them are more than water, but both of them are the same above water. So this one is neutral. Okay, if that was not the case, you would pick the one with the biggest K. So if KB was bigger than KA, it would be basic. If KA was bigger than KB, you would pick acidic, right? Uh-huh.
So what is the math you would do to
This right here, it's the same math twice. KA times KB equals KW.
But you said you'd be given KA.
Well, you would. I'm telling you KA and KB of these two. Because these are not in solution. You're going to get KAs and KBs of these things. Are those things in our solution?
No.
No. You would have a KB for this. You would have a KA for that. But those things aren't in solution. What's really in solution? They're conjugates. So you have to calculate the KA and KB of those conjugates from the values that were given. Does that make any sense? Whatever one you have. Mm-hmm. So let's do one. So let's do an example where we have to actually find the pH. So find the pH of, somebody pick a molarity.
0.27.
0.27. Molar, pick a salt. Let's pick a salt that has to be acidic or basic.
Oh, NaOH.
No, not strong acid. Pick KCl, no, because those are both from strong things. That's just a weak acid. I want a salt.
Aluminum.
NaBr both comes from strong.
NaCl.
Aluminum fluoride.
No.
I thought we were picking
You're picking a salt that would result in an acidic. We don't need to pick the metals in the middle.
NaCl.
Because that's going to mess.
Like one right answer?
No, there's not one right answer.
NaAT. Ammonium chloride.
You can't do chloride. Oh, ammonium chloride. We can do ammonium chloride. Yes, we can do. I thought you said sodium chloride. Ammonium chloride we can do. All right, we'll do that one. So ammonium chloride, because we have to have,
Were all the other answers wrong?
yeah, because all the others resulted in neutral salts. Because you picked a strong base conjugate and a strong acid conjugate. You picked NaCl, right? So they both came from a strong acid and a strong base, so they would have been neutral. Or MgCl or MgBr. They all came from strong acids and strong bases, so they don't, right? It doesn't work. So, all right, so NH4Cl. If we have to find the pH of this, and this is what I would suggest you do every time. What are your major species in solution? NH4 plus, Cl minus, and water. One of those will dictate the pH. Which one? We just did it on the other slide. This one's going to dictate the pH. It's functioning as a what? No, it's functioning as an acid. So how do I write the dissociation of that?
Plus, do you have to do
NH4 goes to NH3 plus.
It's functioning as an acid, so it has to lose an H. Right? It has to lose an H in your reaction. This is an ice table thing. What's the concentration of the NH4 plus?
0.7.
0, 0. It's going to shift right. So minus X, 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 0.27 minus X, X, X. And which K do I use? We know, and what they would give you in the problem is they'd give you the KB for NH3 is 1.8 times 10 to the negative fifth.
So you take one of
Can I use that? That's not in my reaction. That's not what I started with. What did I start with? The acid. So I need to set this equal to K. Well, eventually I have to get my equilibrium line equal to Ka. So I've got to use Kw equals Ka times Kb. So the Ka for the NH4 plus is going to equal 1 times 10 to the negative 14th over 1.8 times 10 to the negative 5th, which we just figured out was 5.6 times 10 to the negative 10th.
Where did you get 1.8?
It had to be given in the problem.
Oh.
Or you had to look it up in a table. It
So
had
why
to be
do you
given.
use the KB of NH3?
Because that's all that's tabulated. When you go look at a table of Kas and Kbs, you're not going to find for these ions. You are only going to find for the weak acid or the weak base. You have to calculate the conjugate's K value, right? They don't tabulate because you can calculate it. So there's no reason to have two tables, right? I don't need a table of weak acids Ks and then another table of its conjugate Ks, right?
Yeah.
So you will only be given for the actual weak acid or weak base. But what's in the salt is its conjugate. So I have to calculate the Ka of the conjugate from that weak base.
But wouldn't you just do 0.27
That's a K value. 0.27 is a concentration. Don't mix up concentrations with equilibrium
minus?
constants
So why do we even need an
because we have to find the pH. I'm not done.
AC?
I'm not done. So Ka is going to equal x squared over 0.27 minus x. And Ka, we just found out, is 5.6 times 10 to the minus 10th. That is definitely really small. So what can we do with this x down here? We can negate that one or assume that one's negligible. Somebody's going to have to solve for x for me on your calculator.
X equals 1.23 times 10
To the negative fifth. All right, so that x is the H plus concentration. So the pH is the negative log of that. So before you punch it into your calculator, you should be able to guess that this pH is 4 point something, 7-ish. How?
Because it's 10 to the power of what?
Right, it's 10 to the power what? Okay, so tell me what the real answer is and then I'll show you. 4 point what? 91. So I was off by a little bit. All right, so here's the thing. In your calculator, punch in the negative log of 1 times 10 to the negative 8th. What do you get?
8.
8.
Punch in the negative log of 1 times 10 to the negative 5th.
5.
5. Now punch in negative log of 2.5 times 10 to the negative 8th.
7.6.
Punch in the negative log of, the negative log of 8.5 times 10 to the negative 8.
7.
7.07.
Yeah, 7.07.
Punch in the negative log of 1 times 10 to the negative 7. See the trend?
Not with the.
Okay, so it should be very obvious when there's a 1 right here.
Yes.
When there's a 1, the pH is the exponent, yes? All right, when it's not a 1, it's just a little lower, right? So if you have to do it in a multiple choice, they're not going to give you options like 7.2, 7.6, and 7.8 as multiple choice answer choices. They're going to give you choices like 7, 8, 7.6, 6.5, right? So that you could clearly pick that out if that was your answer. So
You didn't have to solve it.
you kind of did. You did solve it. You did solve it.
You just don't have to take the extra stuff.
You just don't have to, you just don't have a calculator to plug it in to get the exact answer. But they're not going to give you answer choices that are so close together you couldn't tell without a calculator. Does that make sense? So you should be able to kind of spot that without a calculator. All right, going back to our problem. So now, see how we have 1.23 times 10 to the negative 5th? So it should be less than 5. If you can tell me that, you're good. Okay? All right, are we good on salt?
Is that
I
all you
can-
know about them?
Oh, well, we could make it a little harder, but
As hard as the test will be, that's all I want to know.
we could. What if we had what if we had? Do I want to go there?
If it's going to be on the
If
test.
it's going to be on the test, please go there.
All right, what if there's something already there? What if you add, is it on the test?
Is it on the test?
I don't know. I have to remake your test, so we have to remake yours. Yeah, because your test is not going to include everything mine did, so we're going to have to remake your test. So we did the titrations. The titrations will come off. You will do titrations, but not on this test. Not on this test. You'll do them, but you're not going to do them there. All right, let's skip it for the moment. Since we have the basketball game, let's skip it for the moment. Let me teach the buffers, and then if we have time, we'll come back. Okay, how about that? All right, so let's look at buffers. All right, this should be brand new to everybody unless you've read ahead, and this is in chapter 17. In fact, it's like the first two sections, or maybe 17.2. That's where buffers are. Buffers themselves are not hard. When we add stuff to buffers, it gets hard. That's the part we're going to leave for after this first test. Unless I think your brains can handle it, and then we'll keep going. All right, so definition-wise, anybody know what a buffer is at all? What?
Does it tell if something's changing from an acid to a base?
It does. No, that would be an indicator. So an indicator tells when something's changing from acid to base. That's not a buffer. Anybody know? It doesn't make the solution neutral, but it resists the pH change. So you're kind of right. It doesn't really slow it down because slowing is kinetics, right? And it doesn't make it go neutral. But a buffer, by definition, resists a change in pH. So in other words, I can add stuff to a buffer, and I'm not going to see the pH change all that much. Okay?
Is there like a certain reason why it resists the change?
Yes, it's because it's made up of a weak acid or weak base and its conjugate acid or base. And it will. Like, I'll show it to you in the ice table. I'll show it to you. All right, so a buffer is made up, and this part's if you can recognize this, you can make your life a lot simpler and avoid ice tables. Just saying. It's made up of a weak acid and a salt containing that weak acid's conjugate base. Or it's made up of a weak base and a salt containing its conjugate acid. If that makes any sense. And we'll see it in a second. All right, so some pairs. All right, so give me a weak acid. HF.
How did you do that so fast?
All right, what is the conjugate base of that weak acid? What comes off? F minus. So this is the conjugate, I didn't spell that right. This is the conjugate base of this weak acid. So I need a solution that has the weak acid in it and a salt that contains this conjugate base. So what could that be? NaF. So if I have a solution that contains some concentration of this and some of this, I have a buffer. Okay? So a solution that contains both of those would be a buffer. All right, give me a weak base. NH3 is the most common one. Weak base. NH3. What is its conjugate? NH4 plus is its conjugate acid. So here's its conjugate acid. This is the weak base. So if I had a solution that contained NH3 and a salt containing its conjugate acid, so what would that be? I would have a buffer.
So if you
Go ahead.
okay, so you have to worry about when you're making your salt that it's not another acid.
Yeah. Pay attention that other side is from a strong base or weak or strong base or strong acid.
Okay.
Yeah, make sure the other ion doesn't contribute to the pH. That would be helpful. Yes.
But where did the sodium and chlorine
They're just, I can't go on the shelf and go pick out F minuses, right? There's no chemical back there that's just F minus. They have to come with something. So I need a salt because I need it to dissociate into that F minus. So I need a soluble salt that contains F minus. So we just made up Na. What else could it have been?
So that wasn't part of like the equation where you just added it in for the purpose of making a buffer?
Yes, to make a buffer, you have to have a weak acid and a salt that contains its conjugate. So we could have picked KF and it would have been the same thing, right? Over here, instead of NH4Cl, I could have picked NH4Br. It's just got to be soluble, and it's got to be, the other ion doesn't need to have anything to do with your pH. Right? Okay, so those are buffers. So now you're ready to figure out how do we figure out the pH of a buffer? All right, we're going to start with ice tables, so it makes sense in your head, and then we'll change to an equation. What?
How is HF the buffer when it?
HF is not. The combination of this is a buffer. A solution that contains both of those is a buffer.
Okay.
We haven't really seen how it's going to resist the pH change. Can't do that yet. We got to find the pH of the buffer first.
Me and Christian must fly away.
Must fly away. It's being taped, so you're good. Okay, yes, ma'am.
What would be a wrong answer for that? Would you say it again?
If it's not soluble or if the ion on the front, just pick a group 1 metal and always pick Cl. I don't know. They would be things that did not come from strong acids or strong bases. So you couldn't put, like I wouldn't put NH4F right there. It's a salt. It contains that conjugate, but you also have this NH4 plus kind of fighting with the pH, right? Just make your life simple. The AP test will too. It's not going to confuse you that much, right? They just want to know that you understand the basics. Well, a little more than the basics, but that you understand it. No, if you're making A's and B's on these tests without any extra points, you're on track to make a 4 or 5 on the test. If you're making C's and D's on these tests with no points, you're on track to make a 3. If you're in the 50 range, you're probably going to make a 2, or unless you do a lot of studying. If you're 30s, I don't know, 30s to 50s, no. 30s to 50s actually make 2. Nobody usually makes 1s. I don't have kids make 1s. So that is not a challenge. You do not want a 1. All right, so we need a problem. Let's do an example problem. All right, let's make up an example problem. We're gonna pick our first one, our HF and NAF that we picked. So let's say we have a buffer with 0.2 moles of HF and 0.3 moles of, what did we say, NAF? NAF in a 1 liter container. And I did that on purpose, so I didn't have to worry about mixing stuff and changing molarities, by the way. So I did that on purpose. All right, so what does our ice table look like? Yeah, it's still going to be based on that HF. Let's start here. What are our major species in solution?
H plus.
All right, HF is going to stay HF because it's a weak acid, so it stays together mostly. Okay, what else? How does this exist mainly in solution? Na plus and F minus. And what else is there?
Isn't F usually F2?
Ions came from salt. The salt's dissociating. We don't have gaseous fluorine. Nope, we're not making stuff from nothing. No, the salt dissociates. That's what's floating around at the very, like you throw it all together, that's right what's there, right? So we should recognize that being a buffer. We should recognize that that's not going to control the pH, but these two things are. We should also recognize that they have the common anion, so it's a buffer. All right, so our equilibrium is still the acid dissociation. The only difference in what you did here, what you're going to do here, and what you did on the do now, is now you're going to have a number right there. This is the only difference. All right, so Ka, somebody's going to have to Google Ka for HF for me because I don't know it. Somebody Google Ka.
When do you put the 2 with them?
When it's fluorine gas. Like when it's fluorine by itself.
6.6 times 10 to the negative 4.
It's 6.6 times 10 to the negative 4.
Thanks. It's a chorus now. Okay. So Ka, we had to look up on a table, or you had to look up somewhere, or they had to give it to you in the problem. Of course, on the test, they'll give it to you in the problem. So the Ka for HF is that. All right. Now to fill in our ice table, what's going to go under HF?
0.2.
0.2, because we're in a 1 liter container. If I was in a 2 liter container, what would I put right there? 0.1. Okay, so we're in 0.2 molar. No H plus, but we do have some F minus. How much F minus do we have?
0.3.
Which way is it going to shift? Still shifting right. There's a 0 on the right. It's still going to shift right. So it's minus X plus X plus X. So 0.2 minus X, X, 0.3 plus X. So Ka is, that didn't look very well. Ka, which is 6.6 times 10 to the minus 4, is going to equal X times 0.3 plus X over 0.2 minus X. Okay, A small, what are we going to assume? That this X and this X do not matter because they are added or subtracted to a concentration. We can't get rid of that one though.
So this might. So going back to like last like chapter when we did like Q values and like, so if you did the Q here, it'd be like 0.3 over 0.2, right?
No, it would be 0 over 0.2. 0 times
right,
0.3,
okay.
right? So it's going to shift right because Q is going to be smaller than K. All right, so this simplifies down to 6.6 times 10 to the negative 4th equals 0.3x over 0.2.
Why do we cross those x's again?
Because K is really small, and we don't want to do the quadratic formula. So, I mean, bottom line. The assumption is, though, that it's going to shift right, but it's going to shift right so little. I emailed it to Miss Capel, but he showed up. There was one kid absent, but he checked in, so they're all present now. And I'm babysitting for her. So will you just tell her and get that put in? Thank you. What was I saying? Okay, so solve for x. I don't know what I was saying. What did somebody just ask me? Oh, why can these go away? K is so small, the shift to the right happens, but it doesn't happen enough to change 0.3 and 0.2. It's like taking an 18-wheeler and putting a cotton ball on it. Does it change its mass? Technically. Are you going to notice it? No. So same thing. It's going to shift, but that shift is not going to shift enough to matter to change 0.3. It's still going to be approximately 0.3 and 0.2. The shift is just negligible compared to those values.
But if you can get rid of those x's, can't you get rid of the other ones?
Well, this one, they're negligible because they're compared to something. They are added or subtracted to 0.3 or 0.2, right? So 0.3 and 0.2 are not going to change. But x isn't added or subtracted to anything. So it is its value. So you can't get rid of that one. That one's not negligible. All right, somebody do the math and tell us what x is.
4.4 times 10 to the negative 4.
All right, so x is the H plus.
I got a negative on
So negative log of that gives us a pH of 3.36. Is that what it is? I'm asking. I don't know. I'm not that good. I can't do that math. Okay. So 3.2. So really, it's nothing more than a common ion problem. It's nothing more than a common ion. You had a common ion in solution as this started to dissociate.
So, is the hardest part about this, like, figuring out if you have a buffer or not?
No. The hardest part I haven't showed you. Yeah, I haven't showed you the hard part yet. Uh-huh.
So like the NAF, which is like the random thing that was like not part of the equation, kind of you just look at how
It is part of the equation, though. It is part of the equation because NAF exists as these two ions. That ion is right there. That's why that has an amount in it. Right? That's why the F minus starts with a concentration instead of 0. Right? On your do now, your H plus and your anion started at 0. Right? We put 0 and 0. Because there's a salt in there that has some F minus in it, this now no longer starts at 0.
Okay.
That's the difference. All right, what?
That's a buffer aspect of this part.
That is the buffering part, right? What?
So you cross out the Na plus because it's a strong conjugate base.
It's a very, very weak conjugate acid of a strong conjugate, of a strong base. So it's not going to affect the pH. It's just soluble. It ends up being a spectator ion.
So it has a weak conjugate base.
Yeah, because a strong base, right? We don't even tabulate Ks for strong bases. They are so big, there's no point because we assume it goes to completion. So think about that K of a strong base being really, really huge, like billions of, right? Huge number. If I went to find the Ka of that conjugate, it's going to be teeny, 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 tiny, right? Like almost 0. So that's why that doesn't affect the pH. So because it doesn't affect the pH, we ignore it. Okay, so let me show you another equation you can use. If you can recognize that you have a buffer, you can use the Henderson-Hasselbalch equation. Okay? How are you going to recognize it's a buffer? What does it have to have? A weak acid and its conjugate base in the salt. So a weak acid with a salt that contains the same anion, or a weak base with a conjugate that contains its same cation. All right, so we'll do the exact same problem with the Henderson-Hasselbalch equation. So I don't know, you probably have to write it down somewhere. And I can't spell, so I don't know how it's spelled. Sounds something like that. All right, so it says the pH equals the pKa plus the log, and I don't like it written this way, but I'm going to write it this way, and then I'll show you the way I write it to remember it. I tend to write it as pKa plus the log of the base concentration over the acid concentration. There were people. They're walking. Is that what you're looking at?
He came up and looked through the window and then walked away.
Oh, here?
Yeah.
Who was it?
I don't know.
Who cares? I figured it out.
Why do they send office workers to tell you about things?
Because I don't know. It both interrupts class. I don't know. Don't ask me.
It's looks like an interruption.
Makes that office workers.
It sounds better coming from a kid than it does coming from that to me. So I don't know. Maybe it's just teacher preference. I mean, it aggravates me when they come on that thing and they just talk. Where at least the kid can tell whether he needs to interrupt right that second or not. So, all right, this is the Henderson-Hasselbalch. So let's use it with the one we just did. So pH, first of all, what is pKa? What do you think it is?
The concentration
I mean, it's the negative log of the K.
negative log of that. It's like the
Right. Like pH is the negative log of the H plus, the OH, the POH is the negative log of the OH minus, the pKa is the negative log of the Ka. That's all it is. Okay? So pH is going to equal the negative log of our Ka. What was our Ka value? 6.6 times 10 to the negative 4. Plus the log, what was our concentration of the base? Which one was functioning as the base?
The
F minus was our base, right? So it's 0.3 over 0.2. All right, punch all that mess in your calculator and tell me what the pH is.
Oh, is this just an easier way to figure out?
Mhm.
Yes.
Without the rice.
If you don't like it, you don't have to use it. The ice table will work every time. If you like it,
I don't get
use
what
it.
this
3
is
point,
doing.
what? I got 3.3. Yeah, it's the same thing.
It should be. It should be. 3 point what?
So when you say P, does that just mean negative log?
Yeah.
Basically?
Yeah. Yeah.
No, I just had that same.
Yeah. Click. Uh-huh.
Wait, can you go back to the values? You said 0.3 is the what?
Is the F minus.
And then 0.2 is the H.
Is the HF.
Oh, HF.
Mm-hmm. Is that what you needed?
Yeah.
And sure enough, we got the same pH, so you can do it either way.
Like, if you do like basis, would you like instead of doing log of acid?
No, I do the same thing. I never memorize. You can. I mean, you can change it. I don't. I only memorize this, and if I have a weak base, I simply calculate the Ka and I still put base over acid. As long as you're using Ka, it's base over acid.
Okay.
If you switch, you gotta switch. And I just don't. I memorize one and I just force it that way. Because 9 times out of 10, it's an acid anyway. But I do. That's what I do. You can do it either way you want, but that's what I do. Okay, so there's an equation you can use. As long as you recognize that it's a buffer, you can use that if you think that's simpler. Okay? All right. Can I handle the hard part?
We'll try.
Throw it into solution.
Do you need to?
Throw it into
That means
solution.
we'll be on the set.
Do it.
Let's do titration.
No, not titration. It's just harder buffer part. All right, so how does the buffer resist a pH? We're going to show it to you mathematically. Okay? We have to add a strong acid or strong base to a buffer. That's kind of the problem we're getting ready to do. So we're going to use the same buffer since we already have all that math, okay? We're going to use the same thing we just did. So we have a buffer of HF that we had what did we say? 0.2 moles
Yes.
of that, and we had 0.3 moles of NaF in a 1 liter container. And we're going to add to that some strong base. So let's add, I don't know, let's add 0.1 moles of NaOH to it. Good job. We're on the same path. All right, we're going to add 0.1 moles of NaOH and see what that does to the pH. We already know that the pH of this system is 3.36. We just calculated it, right? We already know that. So now we're going to add 1.1 moles of NaOH and see how that changes our pH. Okay? All right. If we have all of this mess, here's the easiest way to do this. List your major species in solution. I have this buffer, and I've put in NaOH. What are my major species? HF. Na plus, F minus, Na plus again, OH minus, and water. Okay, what happens here is we have this strong base. Do you notice that you see this? This is the hard part, because once you can see this, the math part I can show you.
Real quick, why don't we use NaOH instead of OH? I mean, yeah.
Oh, because when NaOH is a strong base, what does it do in solution? No, it's completely dissociates. So it actually exists in solution as Na pluses and OH minuses. So I'm listing them as they are in solution, mostly. All right, this is going to react with that. The strong base is going to react with the weak acid. The thought process for this is that the strong base reacts completely with the HF. Then the HF is going to be allowed to shift back to equilibrium. So this is 2 problems.
So if you had like a strong acid, it would react with the weak base.
Yeah, you would have a weak base buffer. But since we have a weak acid buffer, we put in a strong base. Okay, so if something reacts completely, is that an ice table or is that stoichiometry? That's stoichiometry. So here's what I do to make my life simple. I still make 2 ice tables, but the first one is a stoichiometry table, not really equilibrium. So the first thing we're going to assume is that the OH minus reacts completely with the HF. So the arrow only goes to the right, right? We can't write the equilibrium arrow. It only goes to the right. So the hydroxide reacts with the weak acid and forms what? Water and some more F minus. Right. Some more F minus. Okay, so what is, and this is going to be my stoichiometry table. I'm going to still set it up like this. You might want to call it F for final instead of equilibrium. This is going to be my stoichiometry table. I'm going to do the stoichiometry table in moles. Now, in this case, it's not going to matter because we have 1 liter of everything, but this table I do in moles.
Why is water on the product side? Because I thought everything, like, the reaction happened in water.
It does, but if an acid and a base react, what do they make? Water and salt. So the H has to come from here and join that, which makes water. So the acid and the base make the water, and then the leftover part of the salt.
How did you know that OH was gonna?
That's the tricky part. Yeah, that's the tricky part. You just have to recognize it. You have to recognize that I have this strong base in here, and I have a weak acid, and acid and base are gonna react. That's practice. That part, unfortunately, it can, but it's gonna react with the most. It's gonna react with the one that will pull off the H's the easiest, which will be the one with the higher K. So
does that mean that if you have a strong acid, then it'll react with a weak base?
Yeah, it will. If we had a weak base buffer, but we have a weak acid buffer in this case. Yes, it would. Yeah. All right. So this is our stoichiometry table.
Good morning, Madison Central. It's a great day to be a Jazz.
I'm going to fill it in while he's talking.
In just a moment, you will hear a bell that will send us to the gym for the basketball game. If you have not paid, you will stay with your second block teacher. Once the bell rings, those of you who have paid can exit class and report to the gym. So that will be the next bell that you hear. Thank you.
Oh, not X. We're not doing equilibrium. It's stoichiometry. So if it's stoichiometry, which one's the limiting reagent? The OH. So you're going to use all of this. You're still going to use 0.1 of that, and you're going to make 0.1 of this. All right, who needs to pay me for that basketball game? All right, so who? Somebody be in charge. Sam, will you collect money so I can keep going on the video? All right, give Sam the money. You're going to make a list. Make me a list. Give Sam your money, and if you're going to the basketball game, go. I'm going to keep writing on the video, so just do that. All right, so the limiting reagent is OH minus because there's only 0.1 of it. So I'm going to use up 0.1 of that. I'm going to use up 0.1 of the HF. I'm going to make 0.1 of the F minus. That gives me 0, 0.1, and 0.4. Agree? Now what's left in solution? I don't know if she's doing any incentive. I don't know. That's why I said write your names down. I don't know that we have to have your names, but.
It's okay.
All right, so now what's in solution? There's some HF. There's still some F minus.
And water.
And water. Is there any, well, there's still Na plus. We don't care about it, but it's still there. Is there any more OH minus? No. So now what kind of problem is it? Ice table, equilibrium. It's a buffer. You can, at this point, use Henderson-Hasselbalch, or you can stick it in an ice table. I'm going to stick it in an ice table. Somebody remember those numbers for me.
Okay.
The 0.1 and 0.4. So HF is now going to be allowed to shift back to equilibrium, H plus. This now is what value to begin with? 0.1. It was in moles, so it needs to be in molarity. This is an equilibrium table. Needs to be in molarity. So 0.1 over 1 liter. I'm just writing it. I know it's still 0.1, but I'm writing it so if it wasn't, you would see it again later, right? All right, what was our value of F minus? 0.4? And again, we're going to put it in molarities, and we don't have any of this. It's going to be allowed to shift to equilibrium, so which way is it going to shift?
Right.
To the right, because there's a 0 there. So 0.1 minus x, if you're not going to the game, you stay with me.
Do we leave our
Sure. Sure. And now we have to have the Ka of HF, which was 6.6 times 10 to the negative fourth. Did I remember that right? Was that the right number?
Yes, yes.
All right, equals x times 0.4 plus x over 0.1 plus, minus x. We're going to ignore these x's.
4x.
So we have 4x, sure. And then when we divide, what do we get for x? Somebody close that door, please. What?
1.6 something times. I'll put 1.7.
Still negative 4?
Yes.
Okay, whatever. Do the math. And then now this is the H plus concentration. So the negative log of that. That's the hard part. This is the hardest problem I can give you.
Wait, can you leave it up?
Can you get, well, after that, can you like go back to one slide?
I will. And actually, we'll do it with Henderson Hasselbalch too. I'll show it to you.
Okay, so this video will be online.
We'll put it online. I'll tell her to put it on your canvas. She can link it on your canvas. Okay. All right, somebody tell me the pH right here. Somebody do the math for me. Oh, 3. I can't read my own writing. That's pretty bad. This is a 4, by the way.
It's like 3.8.
So 3.8. Did it change pH much?
No.
It went from 3.6 to 3.8, and you dumped in a strong acid, right? So it resisted a change in pH. That's why it's a buffer.
It doesn't the strong acid. How did it become more basic?
I mean, strong base. I said it wrong.
Okay.
We dumped in a strong base into the buffer, and it didn't change very much.
I was about to lose it.
Right, we put strong base in, and the pH is still down in the acid range, right? Sorry. All right, so here, instead of doing this ice table, you could have, at that point, used the Henderson Hasselbalch, right? If you didn't want to write out that, just remember these are concentrations, not moles. So here we would have done the negative log of the 6.6 times 10 to the negative fourth plus the log. Oh, my battery's going to die. I'm going to have to stop talking. The log of the base, which is what?
0.4?
The 0.4, because this is the conjugate base. This is the acid over 0.1. And then the pH should come out to be 3.8. Okay, let me stop the video there before my battery dies.